There is one invention hiding inside almost every part of modern life. It wakes you in the morning, runs your car, connects you to people across the planet, and turns a small rectangle of glass and metal into a camera, a map, a library, and a window to the world. It guides aircrafts, delivers medicine, predicts storms, explores distant planets, and powers the artificial intelligence transforming our world today. Yet most of us will never see one, as a modern transistor is so small that thousands of them could be lined up across the width of a human hair and still leave room to spare. Yet they are everywhere, and we could not live today without them. Billions of them operate inside a single advanced processor, switching on and off billions of times every second. Each one performs an incredibly simple task, but together they can calculate, remember, communicate, and create. This tiny device replaced rooms filled with unreliable machinery. It transformed the computer from a tool available only to governments and universities into something billions of people use every day. It reshaped science, business, entertainment, warfare, and human communication. The transistor, the tiny switch that changed the world. And its story begins not inside a modern billion-dollar factory, but with two physicists, a piece of germanium, and a discovery that almost happened in two places at once. In the 1940s, a computer was not something you placed on a desk. It was something you walked inside. Thousands of glowing vacuum tubes performed the calculations. They were large, power-hungry, and about as reliable as an umbrella made from tissue paper. Tubes regularly burned out, and technicians spent much of their time hunting for the latest casualty. But in a laboratory near Paris, two German physicists were working on a device that would help make those glowing giants obsolete. Their names were Herbert Matrier and Henrik Welker. Matrier had noticed something strange while developing radar detectors during the Second World War. If two metal points were placed extremely close together on a piece of germanium, an electrical signal applied to one point could influence the current flowing through the other. After the war, he returned to the phenomenon. Welker supplied increasingly pure germanium, and by June 1948, the pair had produced a reliable amplifier. They called it their transistotron. It had no glowing filament, no glass vacuum chamber, and no need to warm up. It was a tiny solid-state device capable of using a small electrical signal to control a larger one. In other words, it was a switch and an amplifier with no moving parts. At almost exactly the same time, John Bardeen, Walter Brattain, and William Shockley were developing a similar device at Bell Laboratories in America. The two teams had arrived independently at the opening of the transistor age. And now the race was on. The transistotron and Bell's Lab first transistor were point contact transistors. They worked, but they were delicate. Two tiny metal points had to touch a crystal in exactly the right places. Building one was like balancing a pair of needles on a grain of sugar and expecting the result to behave exactly the same every time. It was a brilliant way to prove a transistor could work, but a terrible way to build millions of them. Thousands of transistotrons were manufactured for the French telephone system, but the design was never going to support an entire computing revolution. The first transistor had proved the idea, the next one had to become practical. William Shockley's junction transistor replaced the fragile point contacts with carefully arranged regions inside a single semiconductor crystal. The result was the bipolar junction transistor, or BJT. Instead of balancing metal whiskers on the surface, manufacturers could create three semiconductor layers, either NPN or PNP. A small current entering the middle region controlled a much larger current flowing through the device. The transistor had gone from a laboratory curiosity to something that could be manufactured, packaged, and installed in real machines. During the 1950s, transistorized computers began appearing. They were smaller, cooler, faster, and more reliable than machines built from vacuum tubes. But early transistors were usually made from germanium, which became troublesome at higher temperatures. The industry needed a tougher material. Fortunately, the answer was sitting underneath everyone's feet. Silicon was abundant, handled heat better than germanium, and possessed one particularly useful talent. It could grow a thin, stable layer of silicon dioxide on its surface. That oxide would become one of the most important materials in technological history. In the 1950s, improved crystal growth, diffusion, and doping techniques allowed engineers to place controlled impurities inside silicon. These impurities created the electrically significant different regions that made transistors work. MESA transistors improved speed by etching the device into a raised plateau. But the exposed edges were vulnerable to dirt, moisture, and electrical instability. Then, in 1959, John Herney of Fairchild Semiconductor developed the planar process. Instead of leaving sensitive junctions exposed, the planar process protected them beneath silicon dioxide. Openings could be precisely created in the oxide, allowing impurities and metal connections to be added where required. Transistors were now flatter, more reliable, and, crucially, compatible with mass production. The transistor was no longer merely an object, it was becoming something that could be printed. Even with smaller transistors, computers still required engineers to write thousands of individual components together. That created what became known as the tyranny of numbers. The more parts a computer contained, the more connections it needed, and every connection was another opportunity for something to fail. In 1958, Jack Kilby at Texas Instruments demonstrated that several circuit components could be formed from the same piece of semiconductor material. Soon afterwards, Robert Noyce combined the integrated circuit idea with Herney's planar process and deposited metal wiring. Multiple transistors can now be manufactured and connected on one flat slice of silicon. The integrated circuit, the chip, had arrived. At first, chips contained only a handful of transistors, but once the manufacturing process worked, engineers could repeat the patterns, and repeat them, and repeat them again. While bipolar transistors were conquering early electronics, another branch of the transistor family was emerging. At Bell Labs, Mohammed Atalla and Da Wong Hung built the first successful metal oxide semiconductor field effect transistor, or the MOSFET. Its operation was beautifully simple. A voltage applied to the gate created an electric field. The field opened or closed a conducting channel between the source and drain. The gate did not need a continuous input current in the way a bipolar transistor did. MOS transistors could be made small, packed densely, and operated with very little power. Then, In 1963, Frank Wanlas developed complementary MOS, or CMOS. CMOS paired two kinds of transistors, NMOS and PMOS. When one was on, the other was normally off. Ideally, the circuit consumed very little power while sitting still. Early MOS chips were slower than the best bipolar logic, so technologies such as DTL and TTL dominated many computers during the 1960s and 1970s. But MOS had a superpower. It scaled. As transistors became smaller, designs could fit far more of them onto each chip. CMOS would eventually become the dominant foundation of digital computing. In 1968, silicon gate technology made MOS transistors faster, smaller, and easier to align during manufacturing. The gate itself could help define the position of the transistor's other regions. This self-aligned process reduced wasted space and improved performance. It arrived just in time for the next great leap. In 1971, the central processing unit of a computer was placed into a single commercial chip. The microprocessor had arrived. Around the same period, semiconductor memory began replacing magnetic core memory. Dynamic RAM stored each bit using a transistor and a tiny capacitor. The transistor was no longer simply replacing the vacuum tube, it was swallowing entire computer systems. In 1965, Gordon Moore observed the number of components placed economically on an integrated circuit was increasing exponentially. What became known as Moore's Law was not a physical law of nature. It was an industry challenge, and for decades, engineers kept meeting it. In the 1970s, Robert Dennard and his colleagues described how MOS transistors could be scaled down while reducing voltage. Smaller transistors could switch faster, occupy less space, and for a time, avoid using dramatically more power per unit area. Integration progressed from dozens of transistors to thousands, millions, and eventually billions. During the 1980s, CMOS increasingly displaced power-hungry NMOS logic. Through the 1990s, optical lithography provided even smaller patterns, while chemical-mechanical polishing flattened the chips between layers. Copper replaced aluminium in many of the microscopic wires, and low-K insulating materials reduced unwanted electrical interference. But shrinking a flat transistor could not continue forever. The gate was losing control. By the early 2000s, transistors had become so small that current increasingly leaked through places where it was not supposed to go. Engineers responded with an arsenal of new ideas. Stranded silicon stretched the crystal structure, allowing electrical charge to move more easily. Then, high-K insulating materials, often based on hafnium, replaced the increasingly thin silicon dioxide gate layer. Metal gates returned as well, improving control while reducing leakage. These innovations extended the life of the planar MOSFET. But the flat transistor was approaching its limit. So, engineers made it stand up. In FinFET, the transistor channel forms a narrow vertical fin. The gate wraps around the fin on three sides, giving it much better control over the current. It is the difference between trying to stop a crowd with one rope and surrounding it with three walls. FinFETs entered high-volume logic production during the 2010s. At TSMC, the architecture powered the 16nm generation and continued through 10, 7, 5, and 3 nanometers. Extreme ultraviolet lithography, or EUV, also entered production. It used extraordinarily short wavelength light to print some of the most intricate chip patterns. And by TSMC's 3 nanometer generation, the FinFET had reached its most advanced form. To keep shrinking, the gate needed even more control. The next iteration is the gate all-round transistor. Instead of wrapping around 3 sides of a fin, the gate surrounds the channel completely. TSMC's version uses stacked nanosheets, extremely thin horizontal channels arranged one above another. Engineers can adjust the width of these sheets to balance performance and energy efficiency. The gate's complete grip on the channel also reduces leakage and extremely small scales. TSMC's N2 process became the first production generation to use nanosheet, entering high-volume manufacturing in the fourth quarter of 2025. This is the leading edge today. In 2026, billions of switches whose channels are wrapped inside gates and manufactured with near atomic precision. And the story is still moving. N2P is scheduled to extend the N2 family with further performance improvements. TSMC's A16 technology, scheduled for volume production in the second half of 2026, combines nanosheet transistors with super power rail. Traditionally, power and data connectors compete for space on the front of a chip. A16 moves much of the power delivery network to the back of the silicon, leaving more room on the front for signal wiring. It's rather like moving a city's electrical network underground so the streets above can carry more traffic. In 1948, Matre and Welker placed 2 metal points less than 1/10 of a millimeter apart on a piece of germanium. Their transistortron was delicate enough to be assembled by hand and simple enough to be understood by looking at it. Today, a modern processor may contain tens of billions of transistors, structures so small and complex that no human hand could ever build one individually. Yet, every one performs essentially the same magic. A small electrical signal controls another electrical current, on or off, 1 or 0. The transistor did not simply make computers smaller, it made the modern world possible, because every digital action begins with the same simple decision, on or off. Combine a few of those decisions and you can perform logic. Combine billions and you can build a smartphone, guide a spacecraft, run a hospital, or connect one human mind to another across the planet. By making computing smaller, faster, cheaper, and more reliable, the transistor moved it out of laboratories and into almost every part of our lives. It became the foundation beneath our communication, our science, and our understanding of the universe. All from a switch with no moving parts. A device so small we may never see one, yet so important to the modern world, could not function without it. If you enjoyed discovering how one tiny switch transformed the world, give the video a like and a subscribe for more stories about hidden technology we use every day. And let me know in the comments, which invention should we explore next? Until then, remember, the biggest revolutions can begin with the smallest ideas. Thanks for watching.